So problem A, you're given like T and P, and T is like the time that your phone has been running, and P is how much battery you have left after it ran for that long. And the other thing you have to consider in this problem is that after your phone goes under 20%, the rate of usage of your battery halves. So you can set up some equations where it's like, well, there's like two cases. One is like where P is greater than or equal to 20 and P is less than 20. For greater than or equal to 20, it becomes a lot easier to solve. It's like 100 minus P over T is your rate of usage. And then you can say, for this one, it's like you've been running for, you want to find your total time is actually 80 over R, and then 20 minus P divided by 2R. And then you can solve this, and you end up getting that R equals 80 plus 2 times 20 minus P in parentheses. This is very bad handwriting. Divided by T. And then, so you have R in both of your cases. And you can use that, and also the other thing you need to do to find the answer is like, I call my variables P20, that's actually gonna be. I'll call them D20 and D100, and that's like how long your phone has been under 20% or under 100%, like exclusively. And then you can find these pretty easily in each of these cases, and your answer becomes, what is it? D20 divided by, or 2 times D20 divided by R plus D100 divided by R. So yeah, just some annoying math with casework. We're gonna do that for every.
Are we gonna clap everything?
That's gonna get annoying real quick. Okay, I guess I'm going over the next problem too.
Woo!
Yeah, so in this problem, you are going to build a stair out of blocks. So a stair is like a structure, like these are the blocks I'm illustrating right now. And it's like, the left column is always at least as tall as the right column. So it's like a non-increasing stair. And you want to, what? Okay. So you want to find a stair that is symmetric. So this case is not symmetric, but a symmetric case would be like this. This is a bad way of drawing the stair. Yeah, so here, it's symmetric over, we don't talk about the lines. Okay, so it's symmetric over that. So now you want to construct a stair that uses n cubes, exactly. So here there are like 3 cases in this problem. One is, and this is the one that I did not catch originally, n equals 2. It's impossible. There are no stairs with n equals 2. So you output -1. The other cases are n is even and odd. So for even, I should do odd first. For odd, you can do something like this. And like this is why it's odd, because there's this extra square right here. And, oh, I should have mentioned n is less than or equal to 100. So, and you're allowed to output 100 by 100 grid. So this fits in the grid. And if it's even, you pop this extra square in. So yeah, that is an answer for B. I guess Tyler's next.
So for problem E, we're given some email chain, or we're given like some person's email, and they're given a list of emails. Where if it's a reply, you're going to be given the prefix capital R E colon and a space. So like if we have like a thread that's like 4 long, we would have 3 replies and then some name for the problem or for the email. And we're given I think it's n of these.
It's actually K of them.
K of them, okay. That's what I was trying to remember. I couldn't remember which one was K, which one was N.
Yeah.
So we're given K of these. So let's say we have K equals 3. But we were told that there was originally N equals 3 emails. Let's make it a little bit more interesting. Let's say it's 5. We want to figure out if it's possible to add some number of emails such that we originally had N. Basically, some emails got deleted, and we want to see if it's actually a valid configuration. So what we can do is for each of these like email names, we can store what's the maximum number of replies they have. So we would say that name has 3 replies, which means that this had 4 total emails for it. Then, similarly, second had 2 replies, which means there was 3 emails. However, we see that name had 1 response, but that is lower than what we already have stored for name, so we would only store the maximum value. Then what we do is we're going to go through, add them all together, and then say, check to see if that sum is less than or equal to n.
You don't give a fuck, so Lisa, she gets claps.
Thank you, Andy.
Okay. So problem G was like you're given what we would mostly consider a bracket sequence, but it has like a property where it can be both reversed and kind of unreversed in sections of it. It's like they refer to it as what's the standard German standard notation or something like that,
Polish?
right?
No, never mind. That's something else.
So like, let's see, and then here. Yeah, and so you want to like output the kind of interpretation of this sequence if we were to, I guess, read it properly. Because like the idea is like, imagine if you had it as a regular bracket sequence, is if you could interpret this as a valid like thing you can do as long as they're both reversed. And so like you can do like the range DP and solve this in n cubed because the bounds are small enough. But what you can also do if we use like a kind of, I would almost call it like an inductive argument. You know that they give it to you as doubled, so I just like undouble it because it's the same thing. It doesn't matter. If you like, we know if we read the first character of this that if it is forward, then we have to interpret some section, the first like prefix of our string, as a kind of standard bracket, like non-reversed. And so we can like take it until like the prefix sum of this, of like the +1 -1 kind of idea when you use like bracket sequence, when you approach bracket sequences problem. As soon as this becomes 0, like we have finished a section of our bracket sequence, and now like we have to kind of almost reevaluate again, right? And so like as soon as we reevaluate this next guy, we can again interpret what we have to, like we know what we have to interpret this as, because if we interpret this as a backwards sequence, then we immediately go to -1 in our sum, and so it's invalid. So we know we have to interpret this as forward, and so we can like interpret this one as forward. I think we're actually supposed to output it like this. And then we get to 0 again here, and we see that this is backwards, and so we know that we have to interpret this section as like a reverse section, because if we didn't, then like it wouldn't be valid in the first place. So you can kind of like prove the idea by saying like if you interpreted it a different way, then you would immediately invalidate your bracket sequence anyway. And so if at any point like this becomes invalid, you're supposed to print out that it's not valid. Otherwise, you can just print out the interpretation. Yeah, that's about it. And we can solve it for bigger bounds. Yay!
So problem C, you're given a similar situation to problem B, where you want to construct a symmetric staircase. However, instead of constructing, we want to count the number of ways. So like if we're given n total blocks, where n is up to it was 2 times 10 to the 5th, I believe.
Yeah.
So n is up to 2 times 10 to the 5th. We want to count the number of ways of making some symmetric staircase with n blocks. What we can do is, we're also given like a lot of test cases. Like, what was it, 1,000? 10,000?
10 to the 4th.
10 to the 4th. So we have t test cases where t is less than 10 to the 4th. So let's start by ignoring the test cases and instead try answering this for one query. What we can do is we can form a DP, where our DP is going to store how many blocks we have remaining and what is the current height. And we're going to try building this from right to left. So we start at our rightmost point, and then we're going to say we can do one of two things. We can either place this column, which is going to transition us to dp of rem minus height, and we're going to keep the same height. Or we could transition by changing our height, and we can say we can either, or we can now try increasing our height. For those of you that are familiar, this is similar to what we call partition numbers. However, what we're going to do is, as our base case, what we can do is at any point, well, actually, I think this was all I did for the DP. But the thing that looks weird with this DP is that these look like this is roughly an n squared DP. However, because we know we have to have some form of square here, our height can at most be square root. So really, this DP is order n, square root n. And then now for the test cases, all of our states are going to depend on each other. So instead of running this DP for every single test case, you can store your DP over all test cases, and the number of test cases doesn't end up mattering.
So you like reinforcing the size of your square?
No.
That's what I did.
I don't think you need to.
Yeah, you could do either.
Because I think,
How do you account for symmetry?
this should be, 2 times height. Let me make sure I'm not forgetting something in my solution.
That seems weird.
I feel like I'm forgetting something.
I think you do have to brute force the size of the squares.
I definitely did not. Yeah, no, that is it for my DP. Oh, what I did was at any point for your base case, you could try taking so for the base case, you could say if your height times your height is greater than how much you have remaining, it's greater, then that means we can't place this final square. So then this is impossible, return 0. If it is equal though, then you can instead place this final square and return 1. So you're kind of like brute forcing that final square, but instead like just putting in your base case saying, hey, I hit my final square, return 1, we hit a valid staircase. So that's that problem. For problem D, you're given some pattern string. The string is up to 5,000 long?
Up to 1,000.
1,000, okay. We're given some string, which we'll call S, where the magnitude of S is less than or equal to 1,000. And we're going to try repeating this string until you have k characters, where k is less than or equal to 10 to the 9. And what you want to do is you want to count the number of substrings in this repeated string that are unique. So what we can do is let's start by solving this problem for k is less than or equal to 2 times the length of the string. One way you could do this is by doing the brute force n squared and like brute force all n squared substrings, get the hash of the substring, and check to see how many unique hashes you have. Alternatively, what I did was you can instead do a DP to count the number of duplicate strings you have. You're going to say that dpi j is equal to the number of duplicates such that the first copy ends at I and the second copy ends at j. And then what you can do is you can say that dpi j is going to equal 0 if si does not equal sj. Since we're going to do this for 2 copies of the string, so we really want to do I mod magnitude of s and j mod magnitude of s. And then if they are equal, what we can do is we can say that dp of ij is going to equal dp of I minus 1, j minus 1 plus 1. And this will count the number of duplicate strings. Or sorry, the number yeah, the number of duplicate strings. So then to find how many unique substrings we have, we can go through each prefix of the string and say what is the maximum number of duplicates that occurs in this range, and subtract those out from your total answer. So it's like for I from 0 to the size of s, we're going to say our answer is going to increase by I minus the max value from dp I0 to dp II plus 1. So that would count how many unique substrings are in the first two S characters. 2S or K, depending on which one is larger, or whichever one is smaller. If 2K, however, is less than the size of S, or sorry, if 2 times the string is greater than or less than K, we then need to figure out how to count the rest of the substrings. So what we can notice is that if we call P the length of the period of our string, so the minimum length of the string such that it doesn't repeat. So if we had the string like AB, our period would be 2. What we can notice is that there's some like duplicate patterns going on here. And what ends up happening is that the amount our answer is going to increase in each of these is going to be forgetting the formula that I had. The amount our answer is going to increase will be however many crap, I forgot what I did for this problem, for this part of the problem. What's that? Yeah. So the total amount our answer is going to increase after this is going to end up being the size of our string. Or sorry. It's going to be the size of our total string, so K, minus 2 times our substring length, because that's how many characters we need to like finish computing, times our block size, or our period size. Yeah, because it's for each period, each
period, like each of those distinct starting places in your period doesn't have an overlap somewhere else.
Yeah.
So each of them gets counted for every single length that is with, like in the middle of the range of lengths.
Yeah. Alright. So yeah, so once you get that, you can increase your answer, and that'll be your result.
Good morning, gentlemen. Good morning.
That's my TV. Good afternoon.
That's my fan.
Your fan's right here. This guy's got fans.
Oh yeah, that was funny. As for problem mine, there is some array, or actually it's a list of arrays that you are trying to guess. And you do so by interacting with the judge, not physically, but by asking them questions through the code. And you do that by flushing your output to them. So yeah, the number of arrays goes up to, you can have, I think 1,000 arrays.
Use different marker, please.
We are.
Use different marker.
Yeah.
You have some markers.
Or a red one.
Yeah, let's get red.
Okay, so you can have the 1,000 arrays. Each array is length at most 10, I think. Yeah. And the guesses that you can do is you can ask the judge to give you back the values of basically like you can ask it like a list of arrays to get the values for, but it's gonna give you the values for them not separated in any way. Besides, they also give you the length of each array, but yeah. So let's just run through an example. Let's say we have 3 arrays. First one's gonna be 1, 2, 3, 4, 5. And then we can have one that's like 3, 2. And then actually we can just go with these two. So if you ask it what are the values of both arrays, then it'll give you something like, does it give you the length?
It gives you the total length.
Oh, okay, the total length of all of them.
Yeah.
Okay. So at the beginning it'll be like 7, and then it'll say, so if I ask it 1, 2, it'll say 1, 2, 3, 4, 5, and then 3, 2. But notice I can't tell where 1 begins and where 1 ends. So you need to be smart in what arrays you ask for. And one solution that we came up with, also the number of queries you can give the judge is 20. So, and also you can only ask for at most 1,000 arrays in one query.
At most 10.
Like at most 10, and it goes up to 1,000. So yeah, one solution that we came up with was to do like some palindromic type queries. So if we had these 2 arrays, and also you can ask for the same array as many times as you want in the same query, and the values in each array are pairwise distinct. So those are gonna help you identify the arrays. So basically the solution we had was to do like palindrome. So for these 2, we could ask 1, 2, 1, and then it's gonna give us the total length, so 12, and then these values, 1, 2, 3, 4, 5, and then 3, 2, and 1, 2, 3, 4, 5. No space in between them. But then the way you can extract the arrays is for like going in from like both sides kinda. You can loop through this, and basically once you have your first number, or like you move in both pointers until your pointer on the right matches like the beginning of your left pointer. So we started off with this one. So you want to find the index from the right side that matches this one, and then everything in that range that was covered is in the same array. And yeah, you just keep doing that, moving in till you get all your arrays. So yeah, you can do this in 2 queries, basically asking 1 through 500, but like palindromic, and then like 501 to 1000 palindromic. Yeah.
Here's a question. Here's a question.
What, could you explain that last part again?
The
After.
the 2 queries.
Yeah.
So to get like the whole array, like you can get basically any arrays that you want by doing like a palindromic query and having like another array in between them. So you can ask for the first half and then ask for the solve for the second half. And that's just because we were limited to 1000 arrays in each query. So to do like the palindrome, we need to do like, we can only do like 500.
Yeah.
What's your roll?
Alright,
That's never Snape.
what? Yeah. Just to talk about problem L a little bit, we have a graph.
Oh, you need a different marker.
You're doing J
Oh,
also.
I need a different marker.
Yeah, you're supposed to be doing it there right now.
Oh, sorry. So, got off on the wrong foot, everybody. Just to talk about problem J a little bit, you have a selection of bottles, and basically looks like this. And you have pipes drawn in between the bottles. Well, not drawn; they exist in real life. And what and what you can do is you have a pitcher of water, so it looks something like this, and you can like pour water into the jars, and you're basically going to be given queries of some like destination jar and some like start jar, and you'll pour water into the start jar, and it'll like fill up to some levels, and then it'll traverse through these pipes if it's like above the level, and like fill up these jars to some amount. And so this is the law of the viscosity of luminous liquids or something like that. And basically what you want to do is for these queries, solve for the minimum amount of water you need to pour in the source jar to get even at like a single atom, or I guess you could only go to the molecule level, of water in the destination jar. And yeah, so just to look at the bounds, jars are up to like 10 to the 5th, I think. And you have like Q queries, which is up to 10 to the 5th, I think. And the queries are just these pairs of integers.
It's actually 2 times 10 to the 5th.
Oh shoot, okay. Okay. And then these are less than or equal to n. AI is not equal to bi. Yeah, so how do we want to do this? Okay. Let me remember the solution. So it's basically like when you're looking at these jars, when you look at the destination for some query, what you can notice is the amount of water that's like in each of the jar going from the destination to the source I'm pouring into is like increasing. And it's basically, what it turns out to be is like, I look at these pipe heights, and it's like the max pipe height. I like go back and I take like the max pipe height, and then when the max increases, you basically just have to take like the max pipe height. As you keep going back, if that makes any sense. I can draw a slightly more involved example.
Why don't we get some numbers?
Yeah, that's a good idea. So yeah, let's do that. I can do another one. Let me just erase this. So we can do this, and we can do like here, and here, and here, and here, and this can be like 3, 2, 6, 5, and we're gonna receive here, or we're gonna pour here and like pull here. And basically what'll happen is the height here is basically like 0. We just need to get some amount. The height here is gonna be at 3, and the height here is also gonna be at 3, and then the height is gonna go to 6 and 6 here, I think. Okay, so we're basically like taking a max as we go back, and then like just adding like the max that we've seen since our start jar to get like this sum. And so how do we want to support these queries? Because we need to do something a little faster than like looping through the jars in the range and taking the max like that. So we just have to do that a little bit quicker. Couple ways you could do this. Basically, let me think about this. I gotta come up with a solution. So we could definitely do a stack here. There's a couple things you might think of. It's easy to look at this as a tree. So let's just think about like our parent for some guy. We can just think of all the queries as going one way, like going in here and coming out here, and then we'll just reverse the whole thing, reverse the ranges, and go like back through with the other facing ones. So let's like think of this idea of our parent as like first. Oh yeah.
Wait, so how would you do this naively?
Naively, we will literally start at the source jar
Okay.
and loop like back to the jar we're pouring into, and like add a max of like, we'll take a max of like the height we've seen and like add the amount of water in each one. And then like also we might have to handle some guys over here if we have some like extra jars that just like are connected lower than the connection we're leaving out of and get like sucked back into. But basically that's the idea. We could just also keep looping until it increases again and take those. And so we'll use this idea of our like parent being the first guy to the right who is bigger. So it's basically the first guy to the right who has a bigger height. And now we're kind of like working with a tree, and we want to get the sum on a tree. And so there's a couple ways you can do that. Like you could do that online, binary lifting probably, pre-comp this tree, and then you basically like walk up the binary lifting until you get like past your guy. We can also do offline, so we can DFS the tree with like a stack, and basically keep a stack of like just our ancestors, and then use like those values to answer our query. It's just another way to think about actually sweeping this with a monotonic stack. That's going to be the same thing. Not sure how much I should describe for that. Basically what you'll do is you'll do a stack sweep, and it'll be like a stack that has like the smallest value on top, and you'll like pop these values that are smaller than you on top, and then like push yourself on. So the guy right above you in the stack is your parent, and the guy above him is his parent. So it's basically like you're DFSing the tree, and you have the parents in your stack, and then you also can store for each node the like sum of like this length, and you also know what the height is because it's just your value. This might be some node, and you add like this amount of water for each bucket in the range. And so it's like gonna be like my answer minus some other guys in the stack, like the first guy before this L.
What if
That's the general idea.
What if your parent that you point to that's greater than you is like past the query right index? Like how are you doing with that?
Yeah. So if the parent is like not exactly the node you want to go to, this problem is super nice because that's like exactly what you want, because like the jars, the extra jars between your endpoint and like the actual parent, The jar is not actually bigger, the pipe is. I drew it weird. But the actual the actual parent is like the guy you want to sum up to. Because it's like all these are gonna fill up anyway. So it like just works out perfectly. Yeah. So it just turns out like really nice that it works out perfectly. If you wanted just the sum up to this one, you could do the same technique and like you know what the height would be for this guy because he's like in between two guys in the stack, and then you could basically like look at the length to this guy and subtract those. But they do it super nice to you, so you can actually just subtract that one. The only thing that I found a bit tricky about this one, mostly because I just suck at coding, is because they give like n-1 numbers instead of n. Because it's like these pipe heights in between, and I always find the indexing for that a bit tricky, so I actually had to debug for a bit. I found it a bit tricky. I don't know. Yeah.
I got a question.
Yeah.
Can you explain more about how you do the binary lifting? Like you need to find like basically like all these max points.
Mm-hmm.
But if you're binary lifting, you're like doing jumps like to the end.
Yeah. I think it would probably be helpful to talk about that. So, yeah, we understand the tree. I think everyone understands the tree. It's basically, I'll try to draw a really good picture for this one. And I'll draw out the tree. So you have some heights. Maybe let's do like 5.
So is this like a line tree? Like is this one single line?
It's a straight up tree. So we have 5, 1, 3, 4, and 2. And so there's gonna be like a node in each of these. Oops. Can we see the whole board? We can think of each one as a node. So it's the first guy to the right who's bigger than us. So this guy basically doesn't have a parent. We can create like infinity. I mean, this is an implementation detail. But yeah, this will point to this guy, this will point to this guy, this will point to this guy, and that'll point to that guy. So this is what the tree looks like. And it's basically like, let's say we're querying this bucket. We'll kind of like default over to this node, because this is a kind of our baseline restrictor. Like this is where we're getting water out of. And water is coming in here. So we're gonna like jump. So we go here. Are we past this node? No. And then I guess we jump here. Are we past this node? No. And then I think we jump here. Yes, we're past this node. And so this is the node that we will like end up filling to. And it's basically like this node's sum is gonna include everything from this node, this node's sum is gonna include like basically all the sums on this edge. Like each edge is basically a sum. And so you'll have like what's gonna be added for this edge. So it's basically a path length. We're basically just looking at the path length here. And that's effectively our answer. Because what we're assigning to the path length is like this max times the number of jars on this edge. The idea basically comes down to when we look at the old, like the sort of naive is like we're just walking up, taking a max and adding that each time, right? And so then like all we're doing now is like each edge represents a range with this max, and like we're jumping to the next max each time is a way to think about it. But we can like pre-comp jumps in powers of 2 and then like only take jumps, we like quickly take our jumps.
So when you like make that edge, you're gonna get the distance between the two guys and multiply by the max.
Yeah.
Like, that's the edge range.
Yeah, and that's when you keep your stack, you probably keep like 2 stacks. One is the stack of ancestors, and one is the stack of like path sums, like a prefix sum on your path to the root lengths. And so you'll like add this path to root length, subtract it off, and then it'll be like a difference between path to root lengths since it's you to an ancestor.
How do you convert your starting index and your ending index to like the node numbers you want? Because you don't necessarily want, like you mentioned, you don't want the starting index, you want like the next grader from like before.
Oh, I see what.
Does that make sense?
Yeah, like how do you get the actual place you want to get the
you
sum
wanna
up to?
go instead of.
So in your stack, you'll have like the ancestors, and basically like what you can do is binary search on the stack for like the first. You could just lower bound the stack for the for the first guy who like is after your like pouring endpoint or after your receiving endpoint.
Sure.
Like you find the first guy after, because you'll fill all the way up to him, and then like subtract his sum. It is a bit tricky to think about. Like I'm not gonna lie, I actually had trouble thinking through that when I was implementing this, but I have faith. It'd be how it do, yeah. Just gotta like think about it for a bit. It's tricky. Is everyone good? Okay, thank you.
I'll be going over H. So let's see. So for H, you're given like the king has a certain amount of money and he's died, so you need to split the money among his n wives, because I guess this king is polyamorous. So yeah, so you're to find a way to fairly split money between two people, and that way is if you're given like A1 and A2, which is like how much money they claim that they should get, and the king in fact has this much money, B money, then there are like 3 cases where this is defined. So B is less than or equal to A1, then each person gets B over 2. And then the other second case is, sorry, yeah, B is in between the 2 values that they claim they have. And then you get, first person gets A1 over 2, and the second person gets the remaining amount. And the third case is when the king has more money than each person individually claims they want. And then you get, I don't know why they wrote it like this, because you can like combine the fractions, but that's how they wrote it. And so since there are not 2 wives, there are n wives, you have to like split the money. You're trying to find a way to split the money in such a way that for each pair of people that get, like say each of the wives gets C1, C2, all the way up to Cn money, then for every single pair, the way like for each pair, like Ci plus Cj, if B equals this, and A1 equals Ci, A2 equals Cj, then it's a fair way to distribute the money, and you want to find the value so it's such that this is true. So, and one thing that they do tell you in the problem is that the amount of money that the first wife and the second wife gets, if you do each pair, is monotonic and continuous, which is really useful for this problem. And I think the function looks something like this if you plot it out. Like this is B, this is how much B is, and then some different colors in here. Someone tell me if this is on camera, like is this in the view?
It looks like it.
It is.
Okay. Yeah, and then this is. Oh, okay. It's a bit too steep. There we go. So this would be like how much person 1 gets and this is how much person 2 gets as a function of b. So one thing that you can notice that's kind of annoying is for person 1, okay, I should label these. This is like A1 and this is A2. So this is when like the functions start changing. So for person 1, if they get this much money, you don't really know how much B is. But for person 2, if you know how much money they get, then you can determine what B is using casework. So one thing you can do is, if you assume that, I didn't actually prove this, but if like person 1 and person 2 have their money fairly distributed between them, and person 2 and person 3 have their money fairly distributed between them, and person 1 and 3 also have it fairly. I never proved it, but that is true, proved by AC, you know. So, because like we know that, if we know how much the money the person with the higher claim gets, you can determine how much money the person with the lower claim gets. What I did was I did a ternary search. Is it a ternary search actually? No, it's a binary search. I don't know why I called it a ternary search. It's a binary search on how much money the person with the highest claim gets. So if I say that they get like K, then I can figure out for each pair of people, like each pair with this person, how much money they should get if it was to be fair. And then I can sum all of that up and compare it to how much money the king has. So if it's bigger, then they need to get less money, and if it's smaller, they need to get more money. And then you binary search that until you find how much they should actually get, and you can generate the answer.
So you like, are you kind of keeping it in sort of in binary searching on the person who has the most claim, like how much they're getting,
Yes.
and then working backwards and figuring out the
Yes.
result? Okay.
Yes.
We can know the higher guy, you also know the lower guy.
Yeah. So they actually tell you that n is up to 5,000, but this solution works for, it's in n log, I guess n log n squared or n log max a times n, something like that.
It's n squared log, right?
No, because you don't actually need to try every pair. You only need to try adjacent pairs. Not even adjacent pairs. Like say that like I sorted it, then I just need to do C1 and C2, C1 and C3, all the way up to C1 and Cn.
Should have just been true.
What?
He has a
No.
point.
There's no spanning tree. That's the spanning tree.
But like when you do the it's n log. Okay, cool.
Yeah. So it's actually n log n times max a. Yeah. So yeah, it's a solution. Any other questions?
Yeah, did you also use the multi-protocol label switching for this?
No. I was thinking about it, but I was like, that's too easy, so I went with something else.
Because I was thinking like for the adjacent labels,
Never have I.
also when you sort them, you like switch them. Okay, that's fair.
Alright, Cam.
Alright, we get to actually talk about L. Can play a short game of never have I ever seen an easier problem. Still didn't get it, but it's tight. So what we'll do here, oh wait, we're supposed to explain the problem, right?
Yeah.
So we're given a directed acyclic graph, and what you want to do is label each edge with some color, red, green, or blue, such that there's no path in the directed acyclic graph of length more than 42 where all the edges are the same color. Let me explain what that means. It means if I have two nodes with an edge between them and it's red, and I do this like 43 times, that's bad. So now let me go ahead and explain the solution. Top sort it. This will be our top sort. Now we have top sort. Now, split the top sort into 43 buckets. Okay? No problem. Imagine there's 43 buckets. Now, all the edges, let's just say there's some nodes, all the edges that go like between buckets, we're going to color red. Now I'll use a different color. Now we go into, let's zoom in to this bucket here. And let's say we have these nodes. Well, now we're going to break it up again into 43 groups. And we will, the edges that go between two nodes in different buckets, we will label with green. No problem. Now, one more time, let's zoom into a group. I'll use a different color. We've got a group here. Okay. And we split it again into 43 groups. And all the edges that go like between two different groups we'll label as blue. Okay? So now it's like, it's definitely true that in this graph, no path is going to be longer, of some color, is going to be longer than 42. Because I have, when I take an edge, it puts me into a later group. And then when I take an edge from there, it puts me into a later group. But the number of times I can go into a later group is 42 or something like that. And so, definitely can't have a path longer than that. Oh wait, at this bottom level, what if we have a few extra nodes that are still in a group together? What do we do about those edges? Nah. That's not gonna happen. Because 43 cubed is greater than n.
What is n? You never said what n is.
N is
43 cubed.
50,000. I think so too. So there we go. Well, we know n is less than 43 cubed because AC. Thank you.
Wait, when you say split the group,
Okay.
like topologically sorting it, like you're giving each node a like integer label based off how early it is in the topological sorting? Like,
Yeah. So we have the top sort, and we basically just have like this bucket, this bucket, this bucket, like 43 times. So like the buckets are sized in over 43 like floor or something. And
I know
this
what
is in
top sort
tactile?
Topple sort isn't
I know what top sort. I'm
You
saying
could
like,
use, if you need top sort, you could use tactiles, bro.
yeah. The top sort
I'm
actually.
just kidding. Sorry, what were you saying?
No, like so you're giving like.
I mean, you don't have to give labels. Like, what you're doing is just getting 43, like, groups of equal size.
Write it in base 43.
That's important. That's important so that each, like, group is size at most in over 43.
Okay.
That's important. And so, then you're labeling the edges that span two different groups as a certain color. It's important you make the groups all this size. Don't go putting, like, the first 42 nodes all in their own group and then something silly. You need to leverage the fact that like n over 43 cubed is
That's squared.
less than 1. Anyway.
That's 433.
You know.
So it doesn't seem. Why do we have to use the fact that we're doing like this on a top sort ordering?
Well, because the idea is like, if I take an edge,
Oh, because you can't
it
go
puts
back.
me,
to a
yeah, I
different
can't go
group?
back. It puts me in a later group and I can never go back.
Okay, yeah.
Have you found out, or does anybody else know, like why the probabilistic approach doesn't really?
Oh, I think we had the break case during contest. Yeah, I illustrate it. Like, if you try to do a probabilistic approach,
I guess like the super connected graph on the line.
it's not just like a super connected graph.
What is the probabilistic approach?
Like, if you try any sort of like randomized like coloring the edges or randomized coloring we were trying to like randomize color the nodes and then color the outgoing edges, and like if you try that a bunch of times, you like basically like the probabilistic approach is more like an umbrella term for any sort of probabilistic approach, or at least one that we've figured out so far, is gonna like kind of break in the case where we can imagine like a group of imagine if you have 50,000, and we're gonna split these into layers, right? And we're gonna have that be like 44 layers long, and then each of these layers can interconnect to each other, and then have these groups be as long as possible, so like they could be like 1,000. And what ends up happening is that if you try any random assignment of like the edges or the nodes, the likelihood of you being able to like make it from one layer to the next layer is like super likely, because you only need one pairing to work, and then that means that like you can go and stay like red, because you only need one possible red option to work in this layer. And so
Some
like
birthday
it
paradox.
breaks.
You made a neural network.
Yeah, you make a neural network and then it breaks it, because
Yeah.
like the probability of success just becomes impossible.
One sec. Just to expand a bit on this. This solution's just super good.
Yeah, you could, so for implementation, you could obviously do the recursive deception.
Yeah,
but in a
yeah.
Clean way.
Yeah, so I didn't implement it like that. I bet you're thinking of a pretty clean way.
Yeah, I was asking you.
Yeah, but I feel like you have a good one.
No, I don't.
Alright,
Okay.
we write it as a base 43 number. And find
Yeah.
the first digit that
Yeah, yeah.
differs.
It's basically like, yeah, you can just divide the indices by it, and then like see if they match or something. So it'll be good.
Base 43.
So yeah. Good problem. Let's see more solves on that next time, everybody.
So if I used a number, can I use something lower than 43? Would that work?
Like 40 or something?
Yeah.
Yes.
Anything that like divided by that cubed is gonna be small enough to be fine. So I think they gave a few extra pads there. So I think you could get away with something a little bit smaller. But yeah, whatever the cube would be.
Give yourself F, Andy.
Yeah, but I kinda gotta go to class now.
Okay.
Shoot, bro.
The 2-minute explanation of the problem solved
Yeah.
during this problem review.
Let me give you, I'll just figure on this. So you have a tree, and all the nodes are different colors, so this isn't really accurate. Like you have some other colors. And then you wanna know, like, out of all partitions, where like a partition is like you're grouping some nodes together, and our two partitions are different if two nodes are in the same group in one partition but in different group in the other partition. Then now you want to know over all partitions, over all groups, if we take like the spanning tree corresponding to that group. Like so for example, if I have a group that's like this node and then this node, then we would take this entire subtree, like not just these two nodes. Yeah. So out of all of these groups, the subgraph corresponding to it, we want to know, oh yeah, each node has a color, so it's like a language. So the number of distinct colors on this graph, and then we're gonna take 2 to the k. K is the total number of colors, minus 2 to to the d. I think it's technically plus 1 and plus 1, but that doesn't matter. You can just multiply by 2 at the end. So it's 2 to the k minus 2 to the d. You're taking this and you're summing that up for all groups in this partition, and then overall all partitions. So then there's some linearity of expectations type style thing you do here. Instead of doing it like, okay, let's consider one subgraph, or like one subgroup, not subgraph. So we consider the subgroup of this node and this node, and then we want to know how many partitions is this group in. You kind of just pre-comp that, like based on the number of other nodes. It's like partition numbers kind of deal. Bell numbers, I think. Yeah, it's bell numbers. So for this one, you would take like the bell number 4 and then multiply your so you would get the answer for this graph. You would get the 2 to the k minus d for this graph, and then multiply it by like the bell number for everything that's not in this group. So there's 4 things not in this group, and then you would sum that up for all graphs, for all groups, not graphs. So now what we want to know is for all
For
groups.
all pairs? What are you summing that up for? All pairs of nodes?
All pairs of what? Not all pairs of nodes, all groups of nodes.
Of a specific size?
So like we can take like this group, this subtree, like 3 nodes, and then you would do like
all
bell
like
numbers of 3.
subgraphs.
Not subgraphs, subgroups. Because multiple subgroups can form the same graph.
Yeah.
Like if I take this,
I see what
it's
you
the
mean.
same thing.
Yeah.
and then yeah, there's a trick here you can do. So 2 to the d when you're subtracting, is it no, it's not 2 to the d. It's 2 to the numbers of like it's like 2 to the k minus d. So the number of colors not in the subgraph.
Yeah.
So what you can do is 2 to the k minus d. If you like take all colors not in the subgraph and then just remove them from the tree, then like your subgraph is still connected. So then what you can do is you can like brute force subsets of colors to remove from the tree and like subtract out 1 for every remaining group. And it's like that kind of I don't know how it's not.
That makes so much sense.
Yeah.
I did not think of that, bro.